Well, hello there. This is Dr. Dell again, and this is the Uncle Jack number 6 lesson on geometry. And I'll remind you, if you haven't watched lesson 5, you should, for this to be fully meaningful. In lesson 5, we learned how to create a square angle using the 3-4-5 rule that Uncle Jack had told us about. And then at the end of the lesson, I told you this angle here was a little over 30, almost 37 degrees. It was not a third of a square angle, which is what we wanted, although we had learned how to do half of a square angle, which you'd call 45 degrees. Now in this lesson, I'm going to show you how Uncle Jack taught me to construct an angle that was 1/3 of a square angle. Okay, let's start with a clean piece of paper here. First of all, we construct a square angle here. And this length right here, I used a ruler to measure. It was 3 inches actually. And so what Uncle Jack taught me to do now is to create this is called the hypotenuse. He didn't know what to call it, but this long line here, to be double that. So that's 6 inches. And if you do that, if this is 3 and this is 6, this then is 1/3 of a square angle. Or however you want to put it, 1/3 of a square angle. Now we call it 30 degrees, you know that. Now I will just remind you that in the last lesson, in order to create this right angle, we use this length here, which is called the hypotenuse if you know math, but just this long line here was 5. And so let me pause this video and we'll do that. Okay, so this was 5. And then this angle here was, as we learned last time using trigonometry, was greater than 1/3 of the angle. It was about 37 degrees. So we use, and of course this distance out here in the previous lesson was 4. We used the 3-4-5 rule to, we really did that to get the square angle. But then we created what he called a useless angle that he wouldn't use in construction. And we used trig to prove it was about 37 degrees. And you can see from here that it's clearly a larger angle than this third angle of a square. And so that's how Uncle Jack taught me to do third angles. And by the way, that means this angle up here is 2/3. And he taught me that too. So you could make a 2/3 angle if you wanted to. You would simply go out 3 here and 6 up this way to make a 2/3 angle. Okay, now that is what Uncle Jack taught me. Now I asked Uncle Jack then, as I would do, I said, okay, how long is it from here out to here? And guess what he answered to that? And he gave me an answer. He chuckled and he said, oh, Craig, you're always asking questions, but they're good questions, and you need an answer to it because that's something we'll need to know in construction. And guess how he answered it? Well, Uncle Jack's answer to that question is this distance from here out to here is 17/10 times whatever this length is here. I'll just say L for here. And since in this example it is 3, that would be 17 times 3, which is 21 with 2 to carry is 5. And then you put a decimal point here, and that's 5.1. So this length here is 5.1. Interesting. And that's, I guess it's almost coincidental that it's a little greater than that, but it's 5.1. And he said this is now what he called a close enough answer. And in fact, whenever he said close enough, he meant that it was a little bit short of what was the exact answer. So think about that a little bit, and then we'll come back and look at it with a calculator and see if he was right, if he was correct based on the things that we know today, assuming that you knew the Pythagorean theorem and you knew math and things like that. But this was the answer he gave. Now, I don't know how he knew this. He knew these numbers and could shout them right off to you, and he'd learned them from somebody, maybe a book he had, or maybe somebody told him, I don't know. But he never tried to prove them. He never tried to convince me. He just said, these are facts. And a carpenter that's building things needs to know these facts. So we'll look now in a minute here and think about it a little bit, and then I'll show you why that's true. Well, did you figure it out? Let's say you've got a triangle here, and this is 1. This is a right triangle, and this is 2. So we got our 30-degree angle. Remember, the ratio had to be 1 to 2. Well, by the Pythagorean theorem, what's this length? Well, this length then is 2 squared plus minus 1 squared square root. So it's the square root of 3. Now, in the old days, there were ways to do this manually, but of course that was very arduous to do a square root manually. We don't teach that anymore. We teach a lot of obsolete manual stuff, but that's fortunately not one of them. We use a calculator. We take 3 and we hit the square root, and it's 1.732. And what did Uncle Jack say? He said 17/10, which of course is 1.7000. So it's a little bit less than that. His close enough numbers were always a little bit less than the exact value, and somehow he knew that. So the quick summary, here's what Uncle Jack now had taught us. First of all, how to make a square angle with the 3-4-5 rule. But then if you had this was 1 and this was 1, this angle would be half of a square angle, and this length here would be 14/10. On the other hand, if you made this one and this diagonal, or what's called hypotenuse, if you know the term, but this long side too, this would be a third of a square angle, and this length would be 17/10. Of course, you could turn this up and do it this way. You can make this 1 and this 2 up this way. This is now a two-thirds of a square angle, and again, this is still 17/10. So he knew the 14/10 and the 17/10 were what he called close enough numbers to calculate these other lengths when he needed to. And that was pretty interesting. In fact, he knew a lot of these numbers that he could use then in his construction. And next I'm going to show you what he did with the circle. Now, one other comment before I go to circles. Back in the days of Uncle Jack, when they were doing carpentry work, all they had were hand tools. And they had something called a miter saw where they could actually adjust it to 30, 45, or 60. And then they could cut a 2x4. So if you were building something, and let's say this was going to be a 2x4, you would measure this distance here, and then you use a miter saw to cut the 45-degree angle this way and this way if you were fitting it together. Or if you were using this slant roof, you would use the 30 and the 60 for the 2x4 you're cutting. I'm not trying to teach you carpentry, but that was one reason they used what he called the half square, the third square, and the 2/3 square, because then they had a miter saw that would cut those three things, and so they were constructing it. Now, this he called a good slant roof. He liked to make a roof with this slant because it was relatively, it was just easy to do. It was a good slant. This was a little steeper slant. He didn't like it as well because it was a little bit steeper. And then this was really steep. Now, it depends. If you're going to have a heavy snow load, you might want to build something with this because then it would take less strength in the roof to hold the snow. If you had this, you're going to have more strength, more rafters and things. And he knew all of this. This is carpentry now, common sense carpentry. But these were the slants that he had to have. And I just thought I would comment on that to you, why he was so, I guess they say, stuck on these, what he would call the useful angles. It was because of the hand tools they had of the day. Now, today with modern power tools where you can adjust it to all sorts of angles and everything, this is no longer as critical as it once was. But remember, we're talking about back in the early 1940s. Now, Uncle Jack would occasionally need to use a circle for some reason, and of course, it's very easy to do. You start with a point, and you come out with a piece of string, let's say this length here, I'll call it 1, and then you just move it around like this, and you trace. Say you use a piece of chalk or something or whatever, and you trace this circle. Of course, this is called a semicircle. It's half a full circle, but we're just going to talk about this semicircle. And if we call this length 1 and this length 1, this is called the radius, you may know. I don't know if he knew those terms. I think he did. And then this would be the diameter. The question would be then, what is the length of this circle? If you were going to cut out a piece of wire, for example, and if you want to make it accurate, what would the length be? And what do you think my Uncle Jack told me, and how would you tell someone this? And then I'll tell you the answer. Think about that a little bit. What is that length? Well, he said it's about 3. So I'll put it this way. He said it's about 3. And it's a little bit more than 3. Not much more, but a little bit more. So if you weren't trying to be too close, and let's say you were making say some sort of a flower bed, you would just take whatever this length is here. If this is a 1, then if this was an L, then you would make it 3 times L, and that would be about what it was. He said it's a little bit more than 3, but not much more. So then I got to asking him, I said, well, what if you wanted it more accurate than that? What would it be? And he said, well, close enough would be 3 1/8. He said 3 1/8 for the length would be close enough. And by that he always meant it would be a little bit less than that. And so I thought, well, that was interesting to know. And then he told me an interesting story. He said, well, you know, one time I was talking to a guy, and he told me that this was not a very good answer, because 3 1/8 is, of course, 25/8. And the guy said, no, he said, that's not a good answer. He said, a better answer is 22/7. That's what the mathematicians say. And, of course, that is 3 1/7. And my Uncle Jack said, well, that was kind of funny, because it turns out this is too long here, and this is just a little bit not quite long enough. In other words, he wanted close enough to be a little bit less than the length. So let's look at that and see if we can understand why that is. Get your calculator out and see why my Uncle Jack's answer, from his viewpoint, was better than what some mathematician or math teacher told him was a better approximation. Now, I don't know what age you want to get into this with your child, but it's something you might find interesting. Uncle Jack's answer was 25/8. So we're going to take 25 and divide it by 8, and we're going to see what that is, and that is 3.125. And then we're going to take 22/7, 22 divided by 7, and that is 3.1429. Now, obviously, this is smaller than this. So what is a more accurate answer for this length? Now, Uncle Jack never used the word pi to describe this. Maybe he knew it, I don't know. If you said pie to Uncle Jack, he'd be talking about pumpkin pie, something to eat. But we know, mathematicians know, that this length is very accurately is pi. In fact, on this calculator, we have the letter pi, the number pi. And if you hit pi, that is 3.1416. This is actually a more accurate estimate of that length. Now, you can see that Uncle Jack's was less than that, 0.12 versus 0.14, and the 22/7 was greater than that, 0.1429 instead of 0.1416. Now, it is true that 22/7 is closer to pi than 25/8. It is closer, but it's greater. And Uncle Jack was a great believer that if you want to be close enough, you always want to be a little bit on the short side, for reasons I explained to you in, I think, a previous video, because if you're a little too short, you can fit it in and use a shim to catch up. But if you're too long, it won't fit in. So mathematicians had a more accurate answer than that. And as a matter of fact, our ancestors discovered another fraction that was even closer than that. And I'll tell you what it is. Do you know what is another fraction that's even closer to pi than 22/7? Now, if you look at the history of mathematics, some of our ancestors approximated pi with 25/8, just like my Uncle Jack did. And then others came along and found a more accurate approximation was 22/7, although it's greater. And then some of our other ancestors found an even better approximation, 355 divided by 113. Have you ever heard of that one? Well, go to your calculator and take 355 and divide it. Let's see if I can get it where you can see it. Divide it by 113, and there you get it, 1.1415. Now, that is not exactly pi. In fact, it looks like it might be a little bit less than pi. I don't know. No, it's a little bit greater, I think. Anyway, let's subtract pi and see how far off they are. Here's subtract pi equals, and look how close they are. You got to go out 1, 2, 3, 4, 5, 6, all the way out to here to see the error in it. So that's an extremely more accurate approximation than 22/7. And our ancestors did discover that. Now, quite frankly, that would only be of value if you were making some sort of an extremely precision measurement, which you might be. But it's hard to imagine any precision measurement that would be closer to this and need more precision than that, and certainly nothing that our ancestors back in Uncle Jack's era could do. They couldn't get anywhere near that. So from his viewpoint, this was the best estimate of this of pi, or this length. And I'm just telling you, this is a little interesting background history. And of course, today we have computers that will compute pi out to thousands of places, which of course is way, way beyond any accuracy you could ever use in any physical measurement. So this is Dr. Dale. I will see you on the next video where we'll tell you how Uncle Jack actually worked with fractions and decimals.